Nice.
Alright, so as we go through procedures, recording has started. Alright, first, general plan for the day. Topic number 1 in the general plan of the day is the chemical reactions test apology and update. So, apology goes like this. The test you guys took on Friday was a new test. It was a conglomeration of a couple of units that I put together that I thought meshed well as far as reactions and how they were all based off of reactions and stuff like that. However, not that they were 3 full-size tests, but it was 3 tests that I kind of mashed together. And a lot of times when I make a new test, what I will do is I will take the test by myself first, and then based on how long it takes me to test, I can sort of project how long it's going to take you guys to take the test. I did not do that for this test before I sent it off to the copy center. And as I was sending it off to the copy center and putting it in a little folder, I was thinking to myself, it's kind of long, but I did cut some things out of it that I originally had in it to make it a little shorter. Long story short, I didn't check how long the test was going to take me to take, so that means I didn't check how long the test was going to take you guys to take, and obviously it took a lot longer than it appeared. So anyway, that's why. But as a result of that, and also the fact that there was a couple of field trips on Friday, Mr. Purdy took a field trip, and there was a couple of kids that were out career shadowing, I still have about 6 or 7 kids who haven't taken the test yet. So I started grading them over the weekend. I graded multiple choice questions over the weekend, so I haven't started.
How'd that go?
It seemed okay, all right, I did the multiple choice and like the part where you had to identify the parts of the reactions and stuff. What kind of reactions?
I think I got those.
Anyway, I am going with that, the people making up the test and all that stuff. I'm going to shoot to give you guys back your test on Wednesday during block day. So that's. I might have it done Tuesday night and posted it Tuesday night, but we'll see. Anyway, that's the test. All right. Next, starting today, we have now completed our chemistry unit, and it's time for us to move into the wide world of physics. You'll see some differences as we move from chemistry to physics. Not so much in how class runs, but obviously in the kind of things that we do and the stuff that we're talking about. Last unit that we did on chemical reactions was sort of a culmination of a bunch of different things that we talked about in chemistry. We talked about formulas and unit conversions and equations, and that all kind of came together in the chemical reactions unit that we just finished up. Okay? Obviously, now that we're getting into physics stuff, we're going to have to introduce a whole new set of concepts, and that's what we're going to start doing today. So we're starting simple today, introducing terms, introducing concepts that we are going to use not just through this first unit, but basically through the end of the year. Yes?
Can we have a party on the leap year?
No, we got stuff to do.
Come on. That's like an extra day. It doesn't even count.
That's true, except for the fact that if we get out one day earlier because school is 180 days, it's not like, it's a calendar. So.
No. I think it's going to count.
So, short answer to your question, I mean, if you want to stay...
I'm going to have a party
if you want to stay,
invite everybody in this classroom so nobody will be...
Okay, well then you guys will all have to make up the lab that we're doing.
Oh my god, my dad's birthday just says that.
Can we see the calendars back?
Alright, so Niraj, in reference to the calendar, I've had some problems, not just me, but we have had, teachers have had problems updating websites this weekend. Something is not going right. So, yeah, something wrong with the server. But anyway, I have made the schedule, I just haven't been able to post it. So, here is the schedule. Okay? Starting today, you guys don't have to write anything down right now, just so you know where we're heading. Okay? The blue, we'll get to the blue in a second. Starting today, we're going to introduce our physics concepts and introduce the topic of mechanics. We talk about what mechanics is and why we study it and all that good stuff. Okay? Our discussion from today is probably going to spill over into tomorrow. We'll look at a couple of situations, talk about some applications of stuff, blah, blah, blah. Then, on Wednesday, at the beginning of the class, we'll do some real simple calculations. Plug and chug, here's the formula, here's the numbers, put the right number in the right spot in the formula, give me the answer, okay? But most of Wednesday, we will be on our first physics lab, and that physics lab deals with lab quest. I think we've used the lab clips a couple of times in here, right? We've used it for the temperature, right?
I hate lab.
Okay. We are going to use a different probe on Wednesday. It's a motion sensor, so it measures motion of an object. And we'll talk about how it works and all those good things on Wednesday. There aren't a lot of analysis questions to go along with it. A lot of it is taking measurements and figuring out things from graphs and stuff like that. So that's going to be our plan on Wednesday. That lab will be due on Friday. Also on Friday, you will have your first quiz over this section, over the terms and the concepts that we're going to introduce today. It's an open note quiz, yeah, it's just, making sure we got this basic stuff down. As we go a little bit further, no block next week, okay? Then the following week is OGT testing week, okay? So we are on short periods. School doesn't officially start until about 10:30. Yes, but you guys need to be here at normal time because you guys will be taking practice OGT tests.
Oh my! What are OGT?
OGT stands for the Ohio Graduation Test. And in order
I'm
to...
not graduating.
No, you're not. You're not actually taking the OGT test. Sophomores take the OGT test. You guys are taking a practice OGT test. So, because that's when they give the Ohio Graduation Test, which seems kind of, I know, why what's the use in going at?
It's not graded.
What?
It's not graded. Well, it's like if you don't pass.
So, right. Sophomores, they don't pass one or more. There are 5 parts to it. Yours are not graded. However, Grace, what we do use those tests for is we check and see how people are doing, and if you don't score very well, you may find yourself for the rest of this year and next year getting pulled out of study hall to do OGT prep because you scored poorly on your practice OGT. It's not very hard to fail for you guys.
No, it's like.
So, seriously, if you guys failed, it's probably because you went roller coastered it. You just went ABCD, CBA,
Wait, you said it wasn't very hard to fail. That means it's not okay hard to fail. If it's easy to fail.
The passing, yes, it is timed, but honestly, Sam, you'll be fine.
It's easy though.
You
right?
get 2.5 hours to work on it.
Oh, I thought it was like that other one.
One.
Summer service hours.
So, no, it's not coming.
Are you joking? Come on. You get to go to the lockdown for 5 service hours.
So during this week that is highlighted blue, school does not start officially until I think it's 10:30. So the juniors and seniors will not be here until that. Okay, you guys in this,
Is it the whole week?
yeah, it's the whole week. So there's one test each day. Okay, it always goes in the same order for the sophomores, but you guys will probably be jumping around a little bit. So for other reasons we don't need to discuss right now. But that point being, classes this week are only half an hour long. So you're gonna, Kirsten, I have the test scheduled for that week. We might have to break it up over 2 days. We'll just kind of see how it goes and where we are.
You're putting a test on the days.
Yeah.
Next week. No. Oh.
So we'll talk about it next week. Next week, no block because the teachers who teach sophomores, they kind of want to see their students every day that week because they're taking the OGTs the next week, so they want to do some prep things and stuff like that.
Well,
All right.
want to see it? Or, it doesn't really matter.
I'd rather have block.
Me too, I like that. Because then on Thursday, I have 2 study halls. I have 3 hours to study. What are you scheduling?
All right.
Today?
Here we go. It's already posted up.
No, I mean the stuff that you said.
No, that's up to you.
How do you know?
That's up to you.
But it has to be related to something.
It's a learning opportunity. We discussed this after you guys had that meeting. That in my opinion, you should be able to pretty much do anything you want to as long as you can prove that you learned something from it. Yes. No idea.
I would skip grade right now just so I don't.
All right, let's get started. All right, let's get started. So, up on the board is your opening screen to our first introduction to the wide world of physics. And for lack of a better description, a better definition, physics is the study of the physical world, which pretty much encompasses everything. Okay? Now, with that being said, we're not going to study everything in the physical world. Okay? We're not going to get to that in this class. See how we only have like 3 months or something like that. So, anyway, we are going to start 3.5 months.
So excited.
Plus like spring break.
Spring break.
And the party that we're having on Wednesday.
The party Sam's throwing on Wednesday that you'll all have to make up your lab for. You know, throw that.
So is mechanics the study of everything?
So,
Oh,
no.
Motion.
So, however, when we talk about physics things, we break down physics into different fields because, you know, studying everything is obviously kind of rough. It's like we do in science. We break down things into categories because they're similar. Okay. The first branch of physics that we're going to talk about is mechanics. Like it says up on the board, mechanics is the study of motion. That's where it all starts. The terms and the concepts that we introduce in this section, we will use for the rest of the year to introduce other topics and how they relate to the motion of that object, etc., etc., etc. When we are talking about describing the motion of an object, there are a couple things that we want to know about that object. Let's say you see something cool, I don't know, whatever, you know, your favorite car, whatever that may be, I don't know, driving along the road. And you wanted to describe it to a friend. What are some things you might want to include in your description of that object? Grace? Color, probably that, okay. As opposed, not necessarily the car itself, but the motion of that car.
How fast it goes.
Okay. How fast it goes is one thing you might
How
want to know.
fast can
Speed, okay. How fast it can stop. Okay. Okay. How big it is. Okay. I mean, that's important things. Okay. Now, as opposed to describing the actual object itself, if we talk about the motion of that object, Sam, you brought up how fast it can go and then how quickly it can stop. Those are a couple things that are important there. Okay. But we start off mechanics with 4 questions. And if we can answer these 4 questions, we go a long way to describing that motion that we're seeing. If we can answer these 4 questions, that goes a long way to accurately describing the motion that we see. So first, where? Where is this motion occurring? Second, what is it doing right now? Third, what is it going to be doing in the future? And then the fourth, when are all of these things happening? If we can answer those 4 things, we do a good job of describing the motion of that object. Now we'll see as we go throughout today and into tomorrow that the answers to these 4 questions have specific names. And sometimes there's a couple ways that we can answer this question in multiple ways, depending on what information we're exactly looking for. So we'll introduce some terms and concepts over the next couple of days that answer these 4 questions. Okay. Good so far? Okay. Where do you think we should start? Let's start with number 1, okay? So, okay, Nick, like you said, if we talk about this gecko, okay, here's a gecko. I never quite understood the gecko.
It scares me.
It just kind of like sits there.
Look at his tail
Like,
can fall.
like that.
He put it on and put on my head once.
Yeah,
Oh,
something like that.
that was not.
Like the iguana that's at the door of the wiki lizard.
It's awesome.
Yeah.
Just sits
I
there.
feel bad because
It watches cartoons all day long.
You never.
I think it's awesome.
Anyway,
You can put small kids in there.
regardless. Okay.
Does it run away?
It's in a cage.
Oh.
Put small kids.
Regardless. Okay. All right. Hey. Regardless, if we want to describe this gecko, okay, here's a picture of this gecko, and we're trying to answer the question of where is it, what would you tell somebody?
It's in between.
Okay. Allison says it's in between 0 and 40 on this ruler that we got. That would be fine. Okay, that's a decent description. Okay. So now, one thing that might not be enough, though, Allison, is between 0 and 40 of this ruler, right? But where is the ruler?
Oh.
Okay. So sometimes answering that question of where is the object is not quite as easy as it might seem sometimes. So let's talk about a couple of terms. The first term that we introduce is this idea of position. Okay? Position is the separation between an object and some reference point. If you're watching the video at home, this part is not going to be as good as it is here in the classroom. But let's say we start off with this object. Okay? For those of you that can't see in the back room, that is an Einstein action figure. Okay? And, well, I mean, he was a professor guy. He was like a world-class athlete or anything. Okay? Now, this actually was given to me by a former student. Anybody ever been to Big Fun?
Yes.
Right? Big Fun. There's one in Lakewood, and then there's one down in Coventry and Cleveland. And it's a toy store, but it has all kinds of like crazy toys like this. Now, this I got like I'm gonna turn the lights on for this because you really need proper lit. Sorry about that, but anyway. So not his head, but like it's been like 5 years, and so the glue kind of wears out, so his hair is kind of like removable. So. But he looks so weird that his hair's like an android or something. Anyway, so anyway, let's say, for the sake of argument, and hopefully this really isn't the case, because if it really was the case, this story wouldn't, you'd probably want to hide this fact. But let's say this Einstein action figure with removable hair, okay, is the best thing you ever saw in your life, okay? Let's just say it for the sake of argument, okay? Because if it really is, just like keep that quiet, okay? Yeah. It really isn't that great. But anyway, so you've now seen the best thing you've ever seen in your life, and you have to tell somebody about it. So you call your friend up. Friend, just saw the best thing I've ever seen in my life. Really? What is it? It's an Einstein action figure with removable hair. It's right here in front of me. So your friend says, cool, where's it at? So I can come see it. What are you going to tell him? So, in Mr. Planisec's room, right? Okay? Now, problem, right? I have different rooms. Okay, so room 246. Is this the only room 246 in the world? Okay, at Westlake High School. Now we're getting somewhere, right? So, well, if you want to get somebody, no, Alex, that's the point of this discussion. If you want to get somebody to where something is located, you have to be specific about it, okay? And that's the whole idea of position, the separation between an object and some reference point. Once you've gotten somebody to room 246 in Westlake High School, by the way, this isn't the only Westlake High School out there in the world, okay?
California.
So, right, there's one in California as well. Okay, so anyway, once you've gotten somebody here, now where are you going to tell them to go? Right, there's lots of places in this room. Where are you going to tell them to go? Front desk, blah, 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 corner, on top of the pencil case, all these good things, okay? In order for us to accurately describe the position or other things about the motion of that object, we have to set ourselves up what we refer to as a frame of reference or a coordinate system. Those two terms are used interchangeably. Okay? Frame of reference and coordinate system mean exactly the same thing. And the definition is the context in which we study motion. But there's a couple of things we have to establish first before we start describing either the position or the motion of that object, right? The two things we have to include are a reference point and some directional system. Those are the two things that are required to establish our coordinate system or our frame of reference in order to make sure everybody's on the same page. That's all we're doing here, is making sure that if I give directions to one person and another person, what do I want to happen? If if I want to make sure two of my friends see Einstein, what do I have to make sure that I do at the end of the day?
Talk the same.
They both have to end up where else? In the same place, okay? Now that may be different depending on where they started from, right? But I want them both to end up in the same place. So sometimes that means I might not be able to give them the same directions, but there has to be a framework in which I'm working to get them to the same place, all right? And that's really the whole idea behind the frame of reference, okay? Is that good so far as these first two terms? Okay? Go ahead.
Like, what is the reference?
Okay, the reference point can be anywhere we want it to be, all right? We can pick anything arbitrary to be the reference point. Caroline, a lot of times when we're talking about describing something, we may pick like the starting point of our motion as the reference point. But honestly, you can pick anything you want to, as long as everybody knows that, okay, this is the reference point, okay? Like, if you go to Google Maps, right? Google Maps chooses your starting point of your house as the reference point, unless you tell it otherwise, okay? But it really doesn't matter as long as we make it known.
So, like, if everybody knows that that's where you start, that you just have to make it known that that's what you're
Yes. Yes. And so your reference point can change.
Yeah.
And, Caroline, not to confuse, but you could give a certain set of directions from a certain reference point. Allison could give a certain set of directions from a different reference point, and you guys may still end up in the same spot. And ideally, that's what we would want.
Yeah.
It's just how you define it versus how else define it. Okay. All right. Now, here's where it gets a little tricky. Because if this was the case, if this was the only thing we had to worry about, right, physics would be easy. We just go around and describe where things are in relation to other things.
Well, it's not.
A plus, right? But what happens to Einstein every once in a while? He falls, which is more generally he moves, okay? So we have to take that into account. So what happens if it doesn't stay in the same spot? And the first term that we use to describe that not staying in the same spot is the displacement of that object. And the displacement is defined as the change in position relative to the reference point. If we want to talk about the change in Einstein's position, let's say we're still using our Einstein action figure, okay? What do I need to know in order to determine the change in Einstein's position? Where it is now and where it is then, right? Where does it start versus where does it finish? And I care like that, a lot of times that's in the context of our frame of reference that we've already established. Okay? For example, let's say I really wanted you guys to look at Einstein action figure a little bit more closely, which I don't, but that's okay. Right? So I say, hey, here's Einstein, we talked about him right there, so I give him to Pierce, right? Then Pierce gives him to Nick, makes him to Anthony, blah, 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 goes around the room, okay? At the end of the period, it ends up at Megan, she leaves it on her desk. As you guys are leaving the room, I say, hey, where did Einstein end up, right? And Megan says, oh, it's back here on my desk. Fine. Do I care about what happened to Einstein throughout the course of the period? No. All I want to know is, where did he start, right? Where did he finish? That's displacement. Doesn't matter what happens in between, just where does it start versus where does it finish. Sometimes it's good enough, other times it's not. We'll get into that in a little bit, okay? So let's take a look at a couple of pictures. Pictures that relate to that picture of the gecko that's up at the top of your, right before we introduce position, okay? Now, you don't necessarily have to write this down because we're going to talk about these concepts a little bit more at the picture at the bottom of the front page, so let's just pay attention for now, okay? Let's say I want to talk about this gecko and he starts moving. Okay? In order to calculate the displacement or describe the displacement of the object, we said I needed to know two things, right? What do I need to know? Where he started, where it finished. Okay? A lot of times you will see displacement represented by this notation of delta x, right? What does the delta mean? When we use delta, Dominic, it means what? Change, right? A lot of times we'll use the x because we say that gecko's moving like along the x-axis. What? Yep, up there. That top, yep. We're going to start introducing some of those. Not all of them, but some. So, when we look at the change in position, we want to know where does it start on the x-axis, and then where does it finish on the x-axis. So, where does it start on the x-axis? What's its initial position? 24, right? If we go back to our measurement technique, we know where 20 is, we know where 30 is, right? So 20 is our certain digit, and then our uncertain digit, you know, is an estimation. So yeah, 24-ish, right? And then where does it end up? 85, right? So if we take those measurements and plug them into this formula, right? Okay. 85 centimeters for the final position, minus 24 centimeters as the initial position. That means that this gecko has a displacement of 61 centimeters. Going back to something we talked about before, what's our reference point for this situation here? Nope. What's the reference point here? If I say that this gecko starts at 24 centimeters, where on the ruler? 0 is the reference point here, right? Okay, that's my reference point. Because where does it start? It starts at 24 centimeters. Well, 24 centimeters from where? 24 centimeters from the beginning of the ruler, right? And that's kind of how, that's, you know, in context of this picture, that's what it would be. Okay? All right, are we good there as far as displacement goes? Okay, now let's change it up a little bit. Here's another trick that this gecko takes. Okay? If we want to talk about his displacement, his change in position, we have to know two things, right? What are they? Well, Allison, we technically need to know the reference point in order to figure out where we started, right, and where we finished. Okay? Where did this gecko start? 78-ish, right? And then the final position would be 12-ish, right? So if we plug those in, right? When we do the math on this problem, what do you get? A negative number. Is that okay? Okay. The two things that we need in order to describe motion, the frame of reference, include a reference point and a directional system. Allison, the fact that this is a negative answer, what does that mean in the context of the gecko's motion here? Which way is the gecko moving in this picture versus the previous picture? It's going in the opposite direction. Do we have to distinguish that?
Yeah.
If you really want to describe the motion of something, yeah, you got to tell me which direction is it going. So that's where the directional system comes in. Okay? With that being said, we say that this should be negative 66, right? Okay, when you do the math. Because displacement is an example of something that we refer to as a vector quantity. Okay? And some of you may chuckle in a second when I put up the next thing here, if you make some connections. Okay? A vector quantity tells you two things. A vector quantity tells you magnitude and direction. Magnitude being a fancy word for how much or how big. Direction being a fancy word for which way. Anybody getting that? No? Anybody ever see Despicable Me?
Yeah.
The bad guy, what's his name? His name is Vector. And at the beginning, when he's sitting there with Gru, and then when they're at the bank, and he says that he has both magnitude and direction. His name's Vector. So.
It's bad guy. The guy.
Vector, the guy who makes the squid gun, or squid gun.
Well, I have to go watch that.
Oh yeah. Anyway, so Sam, maybe at your party on Wednesday you could show Despicable Me, and you could like write. You could write it. Maybe you could write it off as service learning.
Yeah.
All right. Anyway, vector quantities tell us both magnitude and direction. Displacement is a vector quantity. means if we're trying to describe the change in position of this object, you have to both tell me how far did it go, but also which way did it go, if you accurately want to describe the motion to me. Okay? Good there? Okay. With that being said, here's a bunch of words that hold on, you have a copy of these words right at the bottom of your first page. Okay? And a picture that goes along with it. So it says, a man starts out from his house and drives east 50 kilometers. After that hour, his car runs out of gas, or after an hour, his car runs out of gas. He walks the next 5 kilometers until he reaches a gas station. He's into the gas station for 30 minutes to fill the gas can and get something cold to drink. He then walks back west 3 kilometers, but then a kindly stranger gives him a ride the remaining 2 kilometers to get back to his car. When he finally reaches his car, he drives back west 50 kilometers to arrive back at his house.
Going in stranger's car.
That's true, right?
Why would he take his house?
Maybe he was on his way to a meeting and his car ran out of gas and he missed his meeting, so he just had to go home. All right. You have this direction, or you have these words. You have this picture at the bottom of the front page. Okay? Now, the questions that are down at the bottom there of the screen actually show up at the top of page 2 of your outline. I apologize for not having this together, but I've got it. Okay? So, let's talk about these questions. First, it says, what is the man's displacement when his car runs out of gas? So, again? In this case, why don't we call our reference point the house? Okay, it's the starting point. We'll talk about, so Chris, that'll be our reference point for this entire problem. Okay? So, what is the man's displacement when his car runs out of gas?
50 kilometers.
50 kilometers, but not just 50 kilometers. Because 50 kilometers this way is different than 50 kilometers that way, right? So 50 kilometers east, right? Because it tells you in the problem that he starts off driving east. Okay? All right. Next question. What's the man's displacement when he arrives at the gas station? Let's talk about his entire trip. So we'll keep the house as his reference point for this entire trip. So Sam, it's going to be 55 kilometers east. All right. Good there so far? Okay. Now here it starts getting a little tricky. Okay? It says, what is the man's displacement when the kindly stranger picks him up? It's going to be 52 kilometers east. Because he's still on the east side of his house, right? Right? Now, if we talk about where he starts versus where he finishes, right? He starts here at the house. He goes this far east, which is 55 kilometers. Then he walks back 3 kilometers. He's walking to the west. But remember we said displacement only depends on where you start and where you finish. So even though he has walked back towards the west just a little bit, where is he in relation to his starting point? He's still on the east side of his house. How far on the east side of his house? 52 kilometers.
He's still farther east.
He's still farther east from his starting point, right? Because we talked about, like, with Einstein, I don't care what happened to him in between. All I care about where he starts and where he finishes. Displacement only takes into account where you start and where you finish. So, the red car started here, right? The car died right about here, okay? He walked 5 more kilometers, and he walked 3 kilometers back this way. But if you talk it in relation to where he started, it's 52 kilometers to the east of where he started. And then for the last question, what's his displacement for the entire trip? 0 kilometers. Because where does he end up? Right back where he started. Okay? Now, if I tell you the displacement is 0 kilometers, does that accurately reflect what has happened to this guy on his trip? No. it tells you where he started and where he finished, and ultimately what happened to him over the course of his day, but it doesn't really describe what happened during that time. So there has to be somewhere else, some other way that we can describe that, maybe in a little bit more detail. And that we refer to as the distance traveled. As far as the definition goes, the distance traveled is the length of the total trip that we have taken between our starting point and our ending point. So the length of the total trip between the starting point and the ending point, which I believe is letter C. Is that correct? Okay. We're going to skip 1 and 2 just for a second because I want to go back to this picture. Okay? So now, these questions again, but we've changed displacement to distance traveled. So, what is the man's distance traveled when his car runs out of gas?
50 kilometers.
Okay, now, in this case, distance traveled is just talking about total length. It doesn't say which direction one way versus which direction the other way. No. So his distance traveled is just 50 kilometers. Okay? Then, the next one, distance traveled when he arrives at the gas station is going to be 55 kilometers. Okay? Because look at your definition here, right? What's the definition of distance traveled? The total trip, right? Okay. Yeah, that's what the second one is. Right? Now, for the third one, right, it's going to be 58.
Oh, 58, yeah, true.
Because how far did he walk? He walked 3 kilometers. Now, in the last case, it was important that he walked back in the other direction. But in the case of distance traveled, it doesn't matter. It's the length of the total trip. He walked 55 kilometers east, then he walked 3 kilometers back west, but his total trip has been 58 kilometers. For the last question, distance traveled for the entire trip,
110.
110. Because he went 55 kilometers east, right?
55.
Right, it's the same story as before, right? Okay. So his total distance traveled is 110 kilometers. Okay? Because as Allison, he went 50 kilometers in his car to here. Right? 5 to the gas station, 3 walking back, 2 riding in the stranger's car, and then 50 kilometers back to his house. Right? Remember that distance traveled is the total length of the path.
Don't you say all the numbers up?
Yep.
But no, but then you do another 50 because he drove back home. So after all that,
You don't add like the 2 as you're getting.
wait, are you adding all these 3 numbers up? And
It's not
No.
just 55.
In relation to the story.
So like 5, 3
No. You add them up based on the story. All right. One more term, then we'll be good for today. Okay? Letters on that page, letter C, number 1. It says distance traveled is an example of a scalar quantity. Scalar quantity up here on the board. Like it says, scalar quantities only indicate magnitude. So underneath letter C, number 1 and number 2. We go back up to where we can.
we heard that. Do you remember when we heard that?
Yeah.
So, scalar quantities only indicate magnitude. So that means they only tell you what? How much or how far, depending on what we're talking about. Okay. And there's a difference there between a scalar quantity and a vector quantity. Are we good there? All right. Hopefully, the website issue will get resolved. There is some things I would like you to look at tonight. A lot of it is reading from your book. Just getting you introduced to a couple terms and stuff like that. Okay. If you want to write it down here real quick. Oh, sorry. There it is.
Page
Some of them you'll be able to answer very well. Some of you might not say do it to things we didn't quite talk about today. So, do your best.
Yeah. Pour it out.
Glad you got that.